Welcome, everyone. Thank you for attending today's webinar about achieving resiliency at any scale with SEL microgrid controls. My name is Jessica Patora. I'm a marketing program manager from Pullman, Washington, and I'll be today's moderator. Before we begin, I'd like to bring a few items to your attention. This is a broadcast-only webinar, and all participants have been muted. Today's webinar will be an hour long, including questions at the end of the presentation. Shortly after, we will post a recording of the webinar on our website. If you have any questions throughout the presentation, please submit them to all panelists with the Q&A tool at the bottom right-hand corner of the application. One of our panelists will review your question and respond to you privately. Any questions that are not answered during the live event will be answered by our experts via email. Our presenter today is Scott Manson. We also have Engineering Services Manager Joe Kassenholz and Automation Project Engineer Brandon Markham joining us today to help answer questions during the presentation. Scott Manson received his Bachelor's of Science in Electrical Engineering from the University of Wisconsin-Madison and his Bachelor's of Science in Electrical Engineering from Washington State University. Scott is the Engineering Services Technology Director at SEL, where he has modeled, designed, and commissioned microgrid control systems for over 19 years. He is a registered professional engineer in 6 states and currently holds 20 patents. Now I'll go ahead and pass the microphone to Scott, and we can get started.
All right, good morning. Scott here. At SEL, our mission statement is to make electric power safer, more reliable, and more economical. To us, safer means protecting those people dear to us, the environment, and those assets with the all-important SEL Protective Relay. SEL today provides more relays to North American electric power utility companies than any other supplier. And as such, we are the popular choice, the single most popular choice for multifunction programmable relays put at the point of common coupling. They are used and programmed by our customers to provide automatic islanding, automatic restoration, load shedding, synchronization, and so many more microgrid functions that are required to provide a reliable power system to your microgrid customers. With programming that can replace a PLC, you can replace a computer with expensive HMI software. You can replace a digital fault recorder, a high-speed data collection event, all with one relay. So it's a very economical, high value add choice that has made us the #1 used device as a microgrid controller in North America. One SEL 751 relay may be sufficient for a single building service entrance job, a microgrid that might contain a battery, a photovoltaic, and a generator. But as you grow your microgrid to include perhaps multiple buildings or a central generation facility, you need to grow both your network and your control system strategy. And for that, we use the SEL PowerMax technology. It's used on microgrids with multiple energy resources, sometimes called distributed energy resources. Hereforth, I'll call them DERs. PowerMax is that fully integrated solution of security, of communication infrastructure, of a microgrid controller, both centralized and decentralized control. It is the single purchase order solution for most microgrids in North America today. We've evolved the solution we call PowerMax into 5 members of the family. The first, the industrial solution, we solved that reliability challenge for our oil and gas customers, the largest projects of which have over 10,000 SEL relays on one job site. In 2002, we tackled the resiliency challenges that these oil and gas facilities had. As you can imagine, on projects such as sour gas reinjection facilities, oil and gas refineries, petrochemical facilities, a power outage can cost tens of millions of dollars, can cause environmental damage, and very readily take a human life. And so these first jobs were a focus entirely on reliability and resiliency. After solving that challenge, we took on the nation-state protection problem. Okay, this is about securing regions of a globe, a country or multiple countries, with a solution that can span kilometers, hundreds of miles, and prevent blackouts in our critical cities, hospitals, police stations, and others. In about 2014, the concept of a microgrid became prime time. And so we scaled down our solution from the industrial and utility offerings to meet the challenges posed by commercial customers like universities, cooperative municipalities, small communities, and more. At this point, we learned how to provide solutions using diverse DERs. This means inverters, reciprocating engines, not just turbines. All the prior jobs were turbines. Now, this is very interesting. These scale of jobs started to scale down around the 1 to 20 megawatt, and many of them included a battery and some photovoltaic. By 2018, we took on another challenge to tackle the kilowatt scale microgrid market. Three-phase 208 is about as low as our solutions go today, but 208 volts, that is. To accomplish this, we performed a complexity reset. And what that meant is we pushed our algorithms into the SEL relays further than we'd ever gone before. We put what was thousands of lines of code into simplified logic in a relay. That was the complexity reset required to scale down the cost and complexity for the mobile market, PowerMax mobile solution. A year later, we realized that there was a major opportunity, and so we merged 20 years of project experience into today's solution we call PowerMax Garrison. For the market in the, again, 1 to 20 megawatt, sometimes kilowatt scale, we've been able to double the features and reduce our prices. And this has largely been accomplished by the plug-and-play technologies and that distributed edge computing that those relays provide us. We've now found that these SEL relays provide a solution that scales from kilowatts to gigawatts. On the vertical axis, you see that as jobs get smaller in size, they move to the kilowatt scale. We push more and more functionality into the relays. This reduces cost and complexity to the size of your project, from one relay to 10,000 relays. It's all PowerMax. Now, for years, SEL has been judged by other parties as the top performing microgrid solution worldwide, both by the Department of Energy and here in this case, Navigant put out a report that clearly showed on the vertical axis that SEL is the top in project execution. We deliver what we promise. The horizontal axis indicates that we're perhaps not the best in sales strategy. I do believe this is an accurate assessment. This is an example of how we use a relay to control an inverter-based resource, or an IBR, with a single SEL relay. Here you see the HMI that historically required a Windows computer is now an embedded graphic that you can program. You now have push buttons for dispatching your DER, the raise and the lower of frequency and voltage, power and reactive power, opening and closing breakers. We'll talk more about the local and remote button, very important button. Enunciation of major alarms on the left LEDs. And furthermore, if you have a check display light flashing, you go see lower tier alarms. These are engine alarms. In this case, it's a Tesla inverter alarm summary. We also have inspection of the internal controls. The relay itself is mostly being used as a microgrid controller, a DER controller. And here are some of the internal set points and control actions that are happening. And we can do fun things with this display as well. If you're familiar with Tesla ludicrous mode, we have it too. Inverter-based resources have created some different challenges for our teams and for our community-based microgrids especially. They've been advertised as a solution to both resiliency and economy. And that can be true if they're integrated properly and if you choose the right inverter-based resource, and henceforth we'll call IBR. But these IBRs have been the #1 challenge of our teams for the last 10 years. IBRs are on battery-based energy storage projects. They're on wind projects, photovoltaics, fuel cells, and anything exotic. Well, most any exotic distributed energy resource will have an inverter. They're required for renewable energy today, and so we really need to get this right. They convert direct current to alternating current. And as you're going to see in the next sections and the remainder of the presentation, we can talk about many of the challenges that not only inverter-based resources present, but others do, and how we solve it with the SEL product line. Now, in the case of inverters, the challenges we're seeing stem from root causes, mostly having to do with human preference, excessive complexity in the firmware, complexities and problems associated with Clark's and Park's transform, such as the DQ transform, the phase lock loops. Please do read the Odessa disturbance report from NERC, very enlightening. Human mistakes, with thousands of settings and thousands of components that go wrong, a small human mistake can create problems with an IBR. Another challenge is that these DERs, especially inverter-based resources, can now act faster than some protection. They're sensitive to different types of loads. The load of a data center is very different behaviorally than, let's say, the behavior of a mine or a rock crushing device. Very different load compositions can cause real problems with IPRs. The very standards we use to select inverter-based resources can also create a challenge itself. Here's an example. Here's a plot taken from an SEL 700G relay, and it shows large, and this is from an event report that extracted out and now is displayed on Syncrowave Event, one of our softwares. This shows an unacceptable frequency oscillation. You see it in the second plot, the middle plot. You see an oscillation in frequency. Now, this caused a lot of finger pointing on this particular job as to whose fault it was. Was it the inverter? Was it the generator? Was it the AVR? Was it the governor? Was it the fuel supply? Very difficult to determine root cause. And how do you find root cause? You use an SEL relay as a truth teller. You capture an event report of all of the behaviors of all of the DERs at the same time, and the truth will come out. Now, inverters, generators, and engines, especially reciprocating engines, and especially inverters, can create harmonics on our AC power systems. For me, I had never decoded the harmonics that I've seen on power systems for decades until recently. And here's a plot that again we produced using our Syncrowave Event software. Again, capturing events from a 700 series relay. And in this case, it turned out not to be an inverter. It turned out instead to be the engine and the generator one. This was a 30 kilowatt generator and engine package. What we've now decoded from this harmonic analysis is that the blue hats, those were multiples of a 15 hertz harmonic introduced by the reciprocating the bang of the piston, quite literally. In this case, these harmonics came from, in this engine, a sticky diesel fuel valve. It was a mechanically fuel-injected engine, and as such, we were able to actually decode which piston was having the problem from the 700 series relay. We cleaned it up. The blue harmonics went away. But what remains, and we're here shown both together, are the purple. Now, these are we've decoded. These are components that come specifically from the generator, not from the engine, and they are from the generator winding. Inconsistencies in pole pitch, in winding construction, in magnetic construction have created on this small generator a rich set of harmonics that need to be dealt with. Now, how do you even know they exist? you have to use a device like an SEL relay, and then software like Syncrowave Event to decode it. I was at a conference recently in California. The number one reason for microgrid failure in California was identified to be integration. Integration is hard. Integration means pulling together inverters, paralleling inverters with generators, paralleling inverters of different manufacturers, point of common coupling discussions with the utility, making sure your relay settings coordinate with the utility, testing everything, dealing with firm up. It's really challenging. This takes skill, but we use relays to simplify our work. We consolidate equipment, multiple pieces of equipment into a single relay. That's a complexity reset. We simplify the user's experience. Look now, when instead of having to a technician or engineer having to understand how to log in with multiple softwares, with multiple laptops, with multiple interfaces to different inverters and generators and battery management systems, you get a top-level display on a relay. The same relay that your utility partners have used for decades. So utilities love to see the solution. Look at how simple it is. Everywhere you go, for every photovoltaic, for every wind, for every battery system, it's the same buttons in the same location. It reduces error. It reduces training costs. It reduces complexity. It's a large value add. Something we need to point out, cybersecurity doesn't have to be complicated. In many cases, the ability to simply turn off a remote algorithm, a cloud-based system, can be your plan B. If you don't have a plan B, use a relay to be your plan B. In this case, by walking to the front panel of this relay, pressing the button to go to local, it immediately cuts off all communication and all controls from any remote system, either it be the local SEL microgrid controller or a SCADA interface, a DERM system, an ADMS, it shuts it off. This is gorgeous. This allows you to have a plan B, a technician in a truck with a radio, drive to the job site, put it in local, and you don't lose power. That is a simple cybersecurity plan B. With relays, seamless islanding, the cost of seamless islanding has been reduced. Many of our customers perceive seamless islanding as expensive because they believe it requires battery. And that is not true. In the very first job we did in 2002, we didn't have batteries, yet we had seamless islanding. How do you do it? Well, you select loads that aren't critical, things like ventilating, heating, chillers, things that you can turn off. And you use SEL relays to turn them off in milliseconds so that when you island, when you separate from the grid, your limited DER's capacity, the batteries, photovoltaics, the generators you have online, can carry your critical load. Now here shown on the screen is what we call the cycle of life. You go from grid-tied operation, and the word automatic decoupling, that's a function of a relay. An SEL relay deciding, hey, the frequency's too low, I need to separate, or hey, I see a fault on the grid, I need to separate. Meanwhile, it performs load shedding. And for a very large project, that relay informs a central controller, a PowerMax central controller, please reduce the load by this amount because you're about to lose it. So this close coupling between a microgrid controller and a relay gives you a very low cost load shedding solution and prevents and in many of the jobs today, people don't have to buy batteries for seamless islanding. They can buy batteries for other reasons. Once you're islanded, and you've done so, a cycle, by the way, a power system cycle is about 16 milliseconds in North America and 20 milliseconds on the 50 hertz grids of the world. So in less than 16 milliseconds, our relays will have asked either a microgrid controller and or other relays to please trip load and equalize load to generation. At that point, you survive. That separation and now survival to an island. It's now the relay's job at the point of coupling to reconnect to the utility power system. We call that a synchronization as engineers. And that, again, is a relay function. That is not a microgrid function. That is a relay function. Integration is expensive. Integration is expensive because of engineering labor. If you've participated in a commissioning job, you may recollect seeing engineers sitting in chairs or on buckets with laptops on their lap for days, weeks, and sometimes months at a time. Well, what are they doing? They're integrating. They're setting up, in many cases, communication between devices and struggling therein to make that communication reliable. Well, at SEL, we use plug-and-play communication between real-time automation controllers. Here shown is an RTAC communicating with an RTAC, publishing saying, hey, I'm a generator. And now the microgrid controller, the 3530-4, says, great, I'm a microgrid controller, so you generator, you start up and go to set point. So now what used to take days, I've experienced weeks and months of communication challenges, is milliseconds. That is a complexity reset. That is a cost saver. That gets you back on budget and helps your ROI. Another challenge we faced in commissioning many projects is conventional use of what's called proportional integral derivative control, PIDs. Used them since the 80s myself personally. And they take time. I still have not yet got the t-shirt that says no PIDs, but I will someday. I don't care for them. Frankly, they've eaten way too much of my time and others' time. And so we attacked this problem with first principles. And with the help of Dr. Ed Schweitzer, we came up with an energy packet solution, a state space energy packet solution that eliminates the PID problems of overshoot, integral windup, presets and resets on the integrals, oscillations. Now it's a setting, not a tuning event. Minutes, not days. In deploying many projects, no two customers are the same. As much as we see the identical power system at one customer, nearly identical from one customer to another, the objectives aren't the same. The perspectives aren't the same. Okay? Their contracts may not be the same. So we need to change not only the dispatch objective per customer, but even more subtly, we need to change the dispatch objective depending on their situation. For example, if you have a storm approaching, you may wish to go what some people call storm mode. We call grid-connected optimal resiliency. Here in this table, it's a selection. It's a table. And the user can select this with our PowerMax solution. But then the storm goes away. It's a bluebird day. Go back to economic optimization. So you can't achieve optimal resiliency and optimal economic at the same time. Repeat that to yourself multiple times. It can't be done. But you can select one mode or the other, or a blended mode. And that's what this table shows you. Up to and including even maintenance mode. You may choose as your maintenance cycle to automatically load test your generators. Let the PowerMax microgrid controller do that for you. One of the biggest questions that any owner of a microgrid needs to answer daily is your microgrid working correctly? Is it achieving the objectives I asked of it? Am I achieving my return on investment? At SEL, we use Synchrowave Operations Historian as the daily dashboard to show us and our customers that we are achieving our objectives. Here you can see a plot from a microgrid put into service. The cyan or light blue line on top is the total load. The brown is the amount of load imported from the utility. And you can see some interesting things happen. This is time synchronized at the relay. So there's no debating that this data is correct because it is correct to the millisecond. And it is time synchronized with technology called C37.118, native to the SEL relay. Built for a much bigger challenge, but perfect for the microgrid market. And now Synchrowave operation being very affordable, it is the optimum historian for the microgrids that we deploy. Here in the bottom, in this particular case, it shows something very interesting. And as an example, the green happens to be a battery-backed inverter of approximately 4 megawatts. During the cycle of its discharge for peak demand shaving, it suddenly turned off. We'll talk more about that behavior in a moment. It turned off. The PowerMax controller then automatically started a 2 megawatt gas reciprocating engine right next to it to compensate for the loss of the battery, still meeting the peak demand shaving objective. Days later, the blue engine, it ran for 1, 2, 3.5 days of demand peak shaving, and the blue engine failed. It had a mechanical failure. It shut off, and during the attempted startup that was requested, and the SEL microgrid controller properly adapted and started a second engine to replace it. This is N-3 failure. This is resiliency. This is simplicity. And this is how you know your microgrid is working correctly. Inverter-based resources create very unusual currents, unusual from the perspective of history. Since Nikola Tesla designed the AC synchronous generator, those waveforms have been well described mathematically for engineers. Inverters don't follow those rules. Inverters can follow the rules of the software coding chosen by the day. And the firmware that's in those inverters is subject to a lot of human error. When you decode those problems, you need a device like an SEL relay that has advanced signal processing to decode. Are those Clark's components correct? Are those Park's components correct? Are the sequence components correct? Is this truly what the inverter is doing? And let me now take this data and go talk to said inverter manufacturer. Please now correct your firmware. This happens daily for us. Inverters also produce a lot less fault current than your conventional synchronous generators, a lot less current transiently. And here, this XY plot, I'm showing that the X double prime is the subtransient reactance that we mathematically simplify a flux-induced event in the air gap of a generator. It's a number. And on average, this parameter that we know since over 100 years is that a synchronous generator produces about 8 times its rated current during a fault, momentarily, then falls off to somewhere around 5 times its rated current during a fault. This is what we call the subtransient and transient reactance effect. Well, inverters don't do that. And that is a paradigm shift. That is a complete shift in how to think about even detecting faults. Can you, for example, see if a tree has fallen on your power line? It can be quite challenging with an inverter because they produce, in this case, the same size inverter, the same 1 MVA inverter next to a 1 MVA generator is going to produce momentarily, for just a few milliseconds usually, 2 per unit current. And that falls off quickly, and then the inverter actually commonly stops commutation. You don't want that. You want the relay to clear the fault before the inverter shuts off. It's a challenge you can solve with advanced algorithms in an SEL relay. Fault currents from batteries, fault currents for low voltage power systems are not always pure reactive current. They're commonly a good component of power producing current. And where does that power come from on an inverter-based resource? Well, most commonly it's going to come from a battery. And if your batteries are out of service, or some of your batteries are out of service, your fault currents are going to be reduced. We've seen this effect time and again where fault currents depend on the health of your batteries. Real shock to us, but this is a solution we now solve with an SEL Axion acting as a battery management system, giving real-time updates to the SEL relays so we can stay in coordination. When you have a variable fault current system, such as in this case, a distribution feeder circuit with a battery electric supply system, a BESS, it has a point of interface breaker and a point of common coupling breaker, and it has many breakers down the distribution line. But we don't have a communication network 20 miles down the line to tell those reclosers and breakers, hey, you need to adjust and adapt your protection based upon the fact that now you aren't connected to the utility. You're connected to a battery because that battery can't produce the fault current of your local utility. How do we fix that? You have the relay, the programmable protective SEL relay, the PPR, tell the battery inverter please shift your frequency. Inverters are great at shifting frequency. They can shift all day long. They don't care. Shift the frequency with the speed of light. Those relays 20 kilometers away now know they're islanded and can switch to a more sensitive protection algorithm, solving a complex problem with the relays that you already own. Inverter-based resources can be faster than the very protective relays you apply to your grid to protect your customers and protect those inverters. And so we like to put protective relays to control the inverter-based resources so that we control them at the right speed. Not too fast, not too slow. Stay in line, and all the coordination works. Here's an example of an SEO relay providing seamless islanding after a three-phase bolted utility fault. In this case, you saw a large surge from the subtransient reactance of the generators on this microgrid. They were both generators, batteries, and photovoltaics. As the fault evolved, currents reduced to the transient reactance currents, and the relay decided to trip, that this is not acceptable. But notice the frequencies in free fall. This microgrid is about to go dark because the frequencies going fast off nominal. This is 1/5 of a second after the event has started. The SEL protective relay at the point of common coupling, typically a 651, in this case it was a 751 relay, opens that breaker. That current is extinguished. The voltage rebounds on the microgrid. You can see the VAB voltage rebound, but not all the way. And the frequency is still in free fall. That's because there's more load than generation, more load than battery, more load than photovoltaic. Your power system's still going to fail. Well, so we use a PowerMax microgrid controller and a relay to shed loads throughout the power system, balancing. And this is the first point I made with that cycle of life. This is that separate, survive. This is resilient behavior done with an SEL protective relay. And the frequency recovers. Back on track, we never lost the power system. That's a happy customer. We also provide seamless reconnection. When a utility fails and you've islanded, you need to reconnect. You can't just close a breaker. You could damage equipment and need to replace it. So we use a relay at the point of common coupling to measure the voltage amplitude difference and the frequency difference, called slip, and then send a dispatch to relays attached to every engine, battery, and even photovoltaics. We measure these parameters at the point of coupling, and the dispatch looks like this. This is a recording right from a BlackBerry phone. Here we go. You can see in the pink line the microgrid coming into phase with the yellow utility. This is dispatched by SEL relays. This is smooth, steady, predictable control, done fully automated. We like to call these a cup of coffee scheme. Press a button, go get a cup of coffee. The relays will take care of it. Inverter-based resources are especially non-deterministic for the many reasons I've mentioned. Here's an example of erratic control on a droop line from an inverter-based resource. Turn that off. Let a relay do the job. Relays are extremely good droop controllers. And so this is the result you get when you replace an inverter control package with mystery meat software with an SEO relay that you programmed. Inverters require a lot of retuning. And this means you need a lot of data collection to know, did that tuning help or hurt the situation? In this case, you see SEL relays being used as high fidelity data recorders, not only with fast sampling from event records from the relay, then extracted to be viewed by Syncrowave event, but also regular streaming C37-118 data held to a historian we call Syncrowave operation. I can't even imagine commissioning a microgrid job without SEO relays and Syncrowave operation. In fact, I don't. And please don't you either. Now, how do you know your microgrid's working? This is a similar question I asked before, but from a different perspective. What does working mean to you? Here on Syncrowave operation, you see we track frequency of multiple generators. You can see some of the frequencies aren't the same. This means that that generator is actually decoupled from the grid. That means it's not participating. That's obvious with the eye. We can see that there's a thermostat that's cycling differently because the cooling water jacket on one machine is behaving differently than the others. Sounds like a call to maintenance to pull that machine out and change that $30 part. So we see phase angles recorded for all time of the microgrid per IEEE 2030.8 standards. You have to record all of these events for the history of the microgrid to meet that standard. We do with this software. Here we record all of the phase angles across the breakers of every synchronization event. You see dispatch set points from the microgrid controller. You see measured powered from all your DERs. Here, there, as these generators turn on and off, we see the dispatch changing. And we can also see network traffic. We can see attacks. This is your preferred dashboard for your microgrid controller. Now, one of the challenges that we face on islanded microgrids is restarting them. How do you re-energize a power system? With generators that can produce 8 times nominal current for that transient surge, it's not been a challenge historically. You just need to have generators started in the right sequence, and they're very forgiving. Inverters are not forgiving. Their design margins are an order of magnitude smaller than the conventional generator. Here's an example of an inverter-backed battery trying to start a small load bank with a fan and a contactor and a transformer that in total equated to half of the inverter's nameplate. What you see is very common with inverter-based resources is that it ramps the voltage to avoid the flux remnants in the steel of the transformer. That's okay. You have to, by the way, separate the inverter to allow it to ramp this, so you can't have your loads attached to this grid. So how do you do that? You use a relay to isolate your loads from your inverter, right? And then even further, what you can see here is even when the load started, you saw the contact chatter as the voltage bounced in and out as you hit the current limit of said inverter. So what this says is that you need to use relays to open breakers, to open contactors, to open building service entrances, to basically add loads in small increments so that you don't overload your inverters. It can be done, and it can be done very simply with just 1 or 2 equations in a relay. And that's a lot simpler and reliable than an expensive microgrid controller. Now, Montclair State University, they found their investment in SEL PowerMax paid off immediately. One event made them true believers, so much so that they spoke on our behalf. So please, after this webinar, please go see that presentation. There'll be links provided to you. Engineers from the country of Georgia, this is not the state of Georgia, the country of Georgia near the Ukraine. Their power system was severely weakened from some events, and they were having blackouts on a regular basis, and so they came to SEL. I remember the day they came to our company and they talked about their challenges, and we found an answer, and that answer was a PowerMax utility remedial action solution using relays to prevent blackouts across an entire country. Good friends of mine in Chevron and at the Tengiz Chevron facility, this is the single largest oil and gas project in the world, again in contentious ground, have very austere environment and require the ultimate in reliability. And so for this very large gas oil reinjection facility, they have selected an SEL PowerMax dispatch, controls, load shedding, and microgrid control system. This is a project you can look up. Please do Google it. There's also a project you can look up. The Presidio, Texas job, circa 2008, was the largest battery in North America at the time. This battery project served a small community on the Mexico-Texas border And to solve their reliability problem which was induced by line outages to their small community, they installed a battery, and the inverter system wasn't resilient enough, not rugged enough, couldn't supply enough current to handle the islanding events. We used SEL relays to detect the faults, isolate the microgrid, load shed non-essential loads to make an unreliable battery-backed inverter into something very reliable. Relays doing their job, not only to island the facility correctly, but to reconnect to AEP, and when necessary, connect to the Mexico grid. Relays do the job and save the day. Saudi Aramco uses a great number of SEL PowerMax control systems throughout their facilities around the world. And at Shaiba, Saudi Arabia, you have a power system which is islanded at all times. Not a small power system, it's actually multiple power systems. And with over 17 large gas turbine engines, all of the protection and control is by SEL and by SEL PowerMax. Very proud that in our discussions with the highly intelligent engineers at MIT, that they also chose an SEL PowerMax system over all other competitors worldwide. They have built, quite frankly, the most reliable microgrid in the Northeast using our PowerMax technology and the SEL protective relay. The Department of Energy ran what I call a microgrid shootout. It was a procurement challenge, I think is the technical name. But in this Golden, Colorado facility, the Department of Energy judged all the microgrid controllers of the world, and SEL was judged the best. So if you're interested in learning more, we have a free hands-on demonstration where you can start a microgrid, run it manually, put it in local, run it as you wish, and then put it in automatic mode and walk away. And what you see during this demonstration is the pinnacle of 20 years of research and projects from SEL. It's an excellent demonstration, 2 hours of your time, and it's free. Please do contact us at selmicrogriddemo@sellink.com, and let's get started teaching. With that, I'd like to thank you for your time. All of us SEL employee owners do respect your time and would very much like your business. If you have any questions, let's please get started. Please put your questions in the chat, and with Brandon and Joe, let's go.
Thank you, Scott. Like you said, we've arrived at the Q&A portion of our event today. As a reminder, like Scott said, please submit your questions to all panelists using that Q&A tool at the bottom right-hand corner of your application. Our panel will respond to your questions privately, or if appropriate, they'll take the theme of your question and answer it generally for the rest of our attendees today. So I'll go ahead and pass things off to you, Brandon.
Okay, thank you, Jessica. Thank you for the presentation, Scott. One particular question I wanted to start with. You mentioned a state space energy packet solution that allows better load balancing and that doesn't require tuning. Can you please expand on that?
Yes. Proportional integral derivative control was designed over 100 years ago mathematically and has been implemented digitally in controllers to this day. When you tune a PID controller, your proportional term, derivative term, and integral term can greatly depend on which state variable you're measuring. Are you measuring speed? Are you measuring position? Are you measuring fuel? All those things which don't change quickly we call states. If you do a little research on electromagnetic transient programming, done also by Hartman loop simulations, you'll find that we integrate against states. But states in our world are things like inertia, things that don't change. Flux. Turns out current isn't a very good state because I can change current instantaneously, but I can't change flux instantaneously. So by understanding the states of your power system, those things that can change quick and that can change slow, you can build and we have built a control mechanism, a control strategy that solves the power system dispatch problem without having to arbitrarily use a control technique designed in 1910, which is what all of our competitors do today.
Awesome, thank you. Secondary to that question, what devices from SEO include energy packet technology?
Today we have implemented portions of it in in the PowerMax Garrison Special Spec 700G relay. We're also offering it in our 735 metering system. If you have a desire for this technology, please do contact us. We will do a consultation and find the right component for you and help you get to an answer.
Thank you. You talked quite a bit about the behavior and reliability of inverters. What is it about inverters that makes them behave so differently than traditional governors? What makes them so much more variable?
Yes, the behaviors of a generator are predicated by the flux and forces in an air gap and the winding structures. That controls primarily the transfer of torque to power and the creation of a back EMF to produce voltage. The engine drives the speed of said generator, and its speed governor, in typically today on the small engine size, they're called engine control units, and they may be digital, more commonly are, but not always. And those speed regulation devices commonly have just simple proportional integral derivative controls. That behavior of a generator is designed into the steel copper design of that generator. It's not arbitrary, and it's been evolved over 100 years. The speed control regulation has also evolved well over 100 years of speed regulation technology, going way back to ball valve governors and even before. The evolution of that equipment is mature. The evolution of inverters is not mature. Instead of engine control units and automatic voltage regulators driving field currents on generators, a inverter transforms its measurement of current and voltages to either a rotating or non-rotating frame. It creates a mathematical mimicry of in-phase and out-of-phase current. It then tries to dispatch for power and reactive power, voltage and frequency, done mathematically, done digitally, done by the human hand. Lots more opportunity for error, lots more opportunity for differences between manufacturers. The differences we see vary between even a manufacturer's different product lines, different size, different era of firmware. We've seen settings changes in inverters from the same manufacturer, the same firmware, also there is a lot more tactile surface for possible changes and human error and misunderstandings. Not everyone's a 20, 30-year skilled power engineer that's trying to deploy an inverter. What does done look like to that engineer? Will they go with what they know? And so we're seeing a lot of inverters that aren't depicting, but could, if they were programmed differently, aren't depicting the behaviors we need for our power system. And it is solvable, but it takes time and education, maturity, and I believe simplification. Many inverters are too complex.
Excellent, thank you. We've had a couple of questions asking where is the demo located?
Excellent question. Brandon, you know this especially well. We are today planning our next tour, January, February, in Virginia, North Carolina, and South Carolina. If you would like to see a demonstration in that area, please contact us immediately. We are planning those events right now. We are having approximately 3 demonstrations a day, 4 days a week, 10 to 12 demonstrations a week over the course of a month in that area. But please do sign up today. Those seats are filling. Thank you.
Thank you. When you talk about seamless transition, what is your time frame? What is your expected time frame for the completion of that transition?
The definition I put out there is seamless means your lights don't go out. So if you have an inverter-based resource with no inertia, no kinetic energy carry through, that means 4 milliseconds. It may not be fully achievable without very high-speed algorithms in a relay. If it's a large utility with many thousands of pounds of rotating steel on rotors acting as your kinetic energy storage, you still need to be fast because you can't run systems through faults, long periods. You will damage equipment. So generally speaking, from the time that we decide to trip an event to the time and trip a point of common coupling, from the time that we decide to trip that point of coupling to the time that we decide to trip a load, we like to see, for the fastest of power systems, around 16 milliseconds. There are some power systems which have enough kinetic energy ride through, you can last as much as 100 milliseconds, like large refineries and some utilities. The irony is that for low cost, well, they're not necessarily low cost, but small microgrids with batteries, which aren't low cost, those battery systems don't always produce inertia. Those inverters don't produce even a virtual inertia, synthetic inertia. And so you have to sometimes act even faster than the electric power system, the mega grid. So anyway, general answer, 1 cycle to maybe 100 milliseconds.
Excellent, thank you. We've had a couple of questions talking about integrating PowerMax with systems that have multiple types of assets.
Yeah.
Diesel, synchronous generators, inverter-based generators, PV, things like that. How does PowerMax work in an environment of varied assets?
Yeah, we are experts at that, and that has taken decades not only to build the skill set of our people, but the algorithms in our products. We put a protective SEL 700G relay is my preferred choice to put on most inverters, and I say most because not every inverter may need it, but the batteries almost always do. You may or may not need them on a photovoltaic. You probably will need them if you've got wind. You will definitely need them at every point of coupling to utility. You'll definitely need a couple for load shedding. You'll need a couple relays at the generators, one per generator. And with that, we use a central RTAC to dispatch the relays, to tell the relays, because we need both real-time measurements from the relays and real-time controls to the relays. Now, those individual relays then, in turn, take those dispatch set points from the microgrid controller and convey them on to their respective DER. Now, if you lose, well, and a common point to make here, and a common challenge is when you're commissioning multiple DERs, you need a incremental style commissioning, meaning you need a small controller for every DER. And so we like to put a relay on every DER to control said DER through the commissioning process. Once he's fully commissioned, it's simply a matter of pressing remote, and it gives control to the microgrid controller.
Okay, thank you. Does the PowerMax microgrid solution require reactors or capacitors with inverters if the inverters aren't already microgrid ready, or if they're older devices?
That's a big it depends. And it's not so much a PowerMax decision, it's more of a harmonic suppression decision. Depends on the inverter. There's many classifications of inverters, from those that are thyristor to IGBT to other silicon carbide to conventional, and they all have their own unique harmonic spectral content and control strategy. So let's have a talk. With that question and many others, we offer free consultations. We have a large team of subject matter experts in microgrids throughout North America. Please do contact us with your project challenges, and we'll get you on the phone with an experienced expert, and we can answer your questions in detail.
Thank you, Brandon, and thank you, Scott, for taking care of all those questions for us. And thank you, everybody, for attending today. We've now reached the end of the webinar. We saw lots of questions coming in, so if your question was not answered live or through that Q&A tool, you will receive an answer from our experts via email, but don't be afraid to reach out if you want more information or did not get a chance to ask your question. If you'd like to learn more about this topic, you can also visit our website. And with that, we hope everyone enjoyed today's event, and we look forward to seeing you all at future SEL webinars. Have a great day.